Right, so let's get down to testing a capacitor with AC to see some of the characteristics and how things work. So what I've gone and done, I've gone and replaced the electrolytic, which we're using with DC, with this nice old variable capacitor with the plates and obviously the air as the dielectric. I've got my decade resistor box over there, and in series with it I've got Jerry's decade resistor project, which I've shown on previous videos, because I don't have 100k resistance values in there, and for this I need to be around 146. So I've got the 100 coming in from there, the 46 on there. It allows me also to easily adjust so I don't have to play with jumpers. And then I've got that obviously coming through. I've got the function generator sitting above here, and that is set for 100 kilohertz. I happen to have it set at 4 volts peak to peak, and I'll bring in closer now so we can see how that changes, and we can also measure the value of the capacitor with the oscilloscope. Right, so I've got everything set up. Obviously the capacitor, variable capacitor here is here. We've got the Agilent oscilloscope, and on here I've set up and I've got dialed in this nice charge wave. Now remember, this is an AC wave, so if I draw out, we'll actually see there are multiple waveforms because we've got an AC signal going in here at 100 kilohertz. Obviously we want to get in so we can see the wave. Now if I go and adjust the resistance, now remember, if I increase the resistance, you're going to get more of a slope because it's taking longer to charge. So I'll just do that. If I go between the two extremes on the one resistor setting, you can see how the slope of the wave changes. Now I've gone and dialed in, just for the purpose of this exercise, 146k. So 146k, and then we get that slope. Now then, I've got the capacitor. I've got the capacitor in its least capacitance value because we've got the plates up, so they're not intersecting each other. Because remember, capacitance in a capacitor is going to increase when you've got a larger surface area of plates. So by moving that dial, I'm going to bring them in, so that in theory I'm going to increase the capacitance. So let's have a look. As I turn this, what do you see? See how the slope of that wave changes? Let me just come out a bit so you can see that a bit better. So if I come out like that and I turn this, there you go. So you can see as we turn that, the capacitance increases, and obviously as it comes back out, it decreases. Now when I say it's increasing, how do we know that it's increasing? So let's just go back and have a look at the formula. If we have a look at the formula, in this case, obviously our capacitance value in farads is related to that time over resistance. Now in this case I'm keeping that resistance constant. So if the time period for the wave taken at that 63.2% mark, if that time increases, then obviously capacitance is going to be increasing. So let's get some measurements on the screen. I'm going to put on the measurements. Now I've got the measurements on here specifically set up to 63%. So if we come in closer to that waveform, what's happening here, these crosshairs and measurements are actually measuring the time over there on the wave, and that is displayed over here. So I'm going to bring you in a little bit closer so you can see that value as I play with the actual capacitor. Right, so I brought you in a little bit closer, and the time which is being measured from the bottom of the kind of wave over here to the 63.2%. Now when I say 63.2, this scope allows me to go to 63%, but the 0.2 for error and the jumping around, the bit of noise I got, is negligible. So we can wipe that out. That's at 63%. And on here you can see it actually gives you a measurement for the rise to that point, and it's bouncing around 8 to 9 microseconds. So between 8 to 9 microseconds. So again, according to that formula, if that increases, then our capacitance is increasing. So now I'm going to turn the dial and just again note what's happening to the wave. You can see the change, and look what's happening to the time. It's increasing, increasing. I'm turning it all the way, almost round. Right, so now I'm at its maximum, and you can see how the time there has actually increased. So we've got a figure of, we're up to now 32 microseconds. I'll turn that back. And there we go, it's gone back to the kind of 8-9 microseconds. So just by turning those plates, we increase the capacitance, and then we come back and you can see how that's affecting the kind of the charge going into and then the actual capacitance value according to that formula. So the next thing I want to do, I'm going to take it to its maximum capacitance, and this time what I want to do, I'm going to pull the wave in so we can see it like that. We want to measure now, what I should note, the measurement that I'm getting now at around 40, between 40 to 43 is a measurement we want to use. Sometimes coming in, I've noted sometimes we get an error coming in, well I say an error coming in close. In theory that should give us a better reading, but for the purposes of this exercise we're going to have a look at this measurement here of around 40 to 43 microseconds. And what I want you to note now is I'm going to change the frequency on the actual function generator, and let's note what happens to the time. Now just remember what we're expecting to happen. As I said, you at some points along the curve, and I don't know where we are on the curve on this particular capacitor, you're going to hit a point where obviously you're going to be increasing your impedance as the frequency increases. And that's obviously due to inductance. Now, as I said, you do get some very fancy LCR meters which will actually graph the response curve of a capacitor, but they cost a lot of money. But you can kind of see the effect of what's going on depending on where we are on this curve, and I suspect we over kind of here somewhere. I'm going to increase the frequency and let's see what happens to the capacitance value. Right, so we're at 1 kilohertz. I'm now stepping up, we're at 2. So the figure we want to keep an eye on, you can see the frequency is increasing because of the waves. Look what starts to happen. We're now down to 30 microseconds, 27, 25. So as I increase the frequency, the impedance is obviously now increasing, and that is reducing the capacity. As I explained earlier, remember, so as we increase frequency, this is going to be going back and forth, creating more impedance, which obviously means less current can flow, so obviously less capacity you're going to get out of the capacitor. So that's what's happening in this example. As I decrease, so we're sitting at 10 kilohertz, just for information. I'm going to come drop back down to 1 kilohertz. 3, 2, 1. Now we're roughly back at our previous reading. So let's get the calculator and do a calculation and see what the actual capacitance is once we're at this frequency with the capacitor set where it is with the resistance that it's got. Right, so I've just gone and typed that into the calculator. So we've got our 40 microseconds, that's obviously to the minus 6, divided by the resistance, which is 146k, so it's obviously to the 3. And that is equal to 273, or near as damn it, 274 picofarads. So obviously you got milli, micro, nano, pico to the minus 12. So there we go, that's how you can go and work out the capacitance by looking at that time space at the 63.2% mark. So now let's go and actually measure that capacitor on a good LCR meter to see if it comes anywhere near that actual supposed measurement. Right, so what I'm going to quickly do is just check that measurement of the capacitor. I've got the Isotech LCR meter over there, which has got very good accuracy in terms of measuring inductance, resistance and capacitance. And I've got it connected at the end of the resistors over there and to the capacitor, so that now it's measuring what we were measuring on the oscilloscope. So we'll just run the test and see what measurement it comes up with. Right, so we're ready, set to go. I'm going to set it to start the measurement. And what it does in this process, I've set it up to do a bit of averaging and to take a few readings so that it comes up with a good result. So it's coming up with 256 pico, which will obviously be which is not far off. So if we look at the calculator, we were sitting at 273. But recall when I was messing around with the measurements, I was kind of noting to go with the kind of 40, it was bouncing around 40 to 43 microseconds. And I actually probably got a better reading when I went in. So I was being silly. So let me just adjust that. That reading was around, if I recall, around 38. And again, you can double check me on the previous video. But if I put in now 38 microseconds, heavens, so now it's certainly not far off at all. So now we're sitting at 260 pico and we've got 256 pico. So what was being shown on the scope in that example certainly isn't far off by literally being able to do those measurements by knowing the time period and knowing the resistance. Right, so now let's have a look at capacitors in parallel and in series. So you might be in a situation where you need to calculate and understand how capacitance values change when you link them up in either parallel or series. You might have an instance where you actually want to have capacitors in parallel. Let's say you want them to share the workload, because one of the things you need to be careful of in certain environments, whether there's heat or the current going through them. So you may well want to run a configuration like this. So it is the inverse of resistance. So obviously resistors in series add up, but for capacitors, if you have them in parallel, they add up. So in this case, you can see we've got C1, C2, C3 in parallel. C total, as in the capacitance value total, is C1 plus C2 plus C3, or more if you obviously have them. And if we go over to series, there's a few examples here that basically if you've got two capacitors in series and their values are the same, so C1 is equal to C2, then C total will just be, let's say, the one value over 2, so half. It's a half of one of those values. If you have just two in series but their values are not equal, then you can go by the formula C total is C1 times C2 divided by C1 plus C2. And again, you should recognize some of these from resistors in parallel. Okay, but remember, this is series for capacitors. If we have a situation where we've got more than two, C1, C2, and C3 in series, well then you're going to go to C total is equal to 1 over the reciprocal of each of the values. So it's 1 over C1 plus 1 over C2 plus 1 over C3. So those are the formulas you can use to calculate the value of capacitors in both series and in parallel. Right, so let's just do a practical demonstration on connecting the capacitors in either series or parallel. So I've got two identical capacitors here. We're going to measure them on the LCR meter. The first one I've got in the breadboard there. The value of these is around 330 microfarad, but be aware that the tolerance level on these is not great. So let's just check the value of the first one. So we've got just over 3000 farad. So what I'm going to do, I'm going to connect this one in parallel. So there we go, I've got them both in parallel, and what we expect here to happen is the capacitance value to increase because they're going to sum together. And there you go, it's not quite up to 6000, but we don't know exactly what the value of this is, and obviously tolerance might be playing a part. So let's see what happens when we go into series. Right, so now I've got them in series with each other, with the leads across the kind of either side of it. And now if we go and check, what are we expecting? And there you go. It's gone to half the value of that first one that we actually measured. So that's a practical demonstration of what happens with capacitance in both series and parallel. Right, now one of the kind of obvious things or applications of capacitors to cover is filtering, decoupling. Now I do have a video which I'll annotate or have a link to in the details below, where I go through demonstrating how capacitors help in filtering in an AC to DC power supply. So I'll link to that because there's calculations in there and you can actually see the practical application on an oscilloscope as well. But here we want to talk about capacitors in decoupling and how they work. So decoupling basically can help you where you've got a situation where you in essence want to remove noise or pull noise down to ground to pull noise out of a circuit. Now here's an example of decoupling, let's say in a power supply unit. Let's say we've got a power source over here, and you potentially might have some noise, or your load might be of varying load and working at a certain frequency, but you wanted to see a clean load. Or you can put a capacitor in here, a larger value capacitor, which is going to act as a kind of supply and filter. So in that situation, if you've just got that capacitor, if you suddenly have a larger load over here being pulled, you're not going to have your voltage necessarily drop down, because the capacitor can, for a short period of time, supply current to the load. You could have a situation where your load over here, if it's working at a certain frequency, might be generating noise, and again you want to kind of pull that noise out of the circuit. And remember, because we've got a DC supply over here, that DC is not going to go down to ground and short, because the capacitor is going to block it, as we've seen before. Now in this situation over here, where you could have some high frequency noise, i.e. some AC going up, down and over here, which you want to remove, if you put a smaller value capacitor, and of course when I say smaller value, there are calculations to understand depending on the resistance values, the frequency that you're dealing with, to work out the capacitance value. But here, as you can understand, if you've got that high frequency AC going back and forth, that will be passed through the capacitor and taken down to ground and removed for the most part. So there's a really handy use for capacitors in terms of decoupling. So you'll often see these in circuits, you'll have decoupling capacitors. There are of course loads of other uses for capacitors. They really are a handy device. But the one thing before we leave this circuit I want to highlight, I mentioned here, what about using inductors? Now inductors will be the next thing that we have a look at in the electronics tutorial, because before we go into let's say transistors and digital electronics, they also play an important part. Now one other way to obviously filter here, and this is where capacitors, resistors and particularly inductors work well together. What if we had to add an inductor to the circuit over there? Now some of you might recognize this straight away, but an inductor does the opposite to what a capacitor does. Let's say again we really wanted good sensitive noise filtering in the circuit to protect our load over here. Well, if we had noise coming out over here, an inductor resists noise. So it will resist the AC component, so it'll block it from going along here, whereas obviously the capacitor is doing the opposite. So that's why it's in series over here, and this becomes a pi filter. And we'll be looking at these and talking about filters, because obviously both capacitors, resistors and inductors, depending on how they linked up in whatever network, we've got a pi network here, can prove very handy in terms of passing certain frequencies, blocking certain frequencies and eliminating noise. So this is something we're certainly going to have a look at in videos to come. Now the other important application that I wanted to note, just mention, because just these simple devices, because of their time basically having that RC time component, leads us also into digital electronics, because I've discussed or mentioned ADCs, analog to digital converters, and in those this is a very simplified look at an ADC. But if we have an analog signal coming out, and obviously we're expecting a digital output, the RC time component of a capacitor is used in conjunction with a counter to basically take levels and then get your digital reading out. Now it really is an oversimplification, but I must say, just when you start looking into how ADCs work, you'll realize how the role of a capacitor is critical as a timing device in that, which leads us in from the analog world and into the digital world. Right, so what are the key things we need to know when choosing capacitors for your application? Now, as I said, you get loads of capacitors of all varying types and sizes. They've got different dielectrics and all sorts. So rather than going through the types, what you need to be aware of and then to go and check on a data sheet are these items. Now, for one, obviously, you need to work out what capacitor you need. So that's going to be the obvious thing. The next thing is the voltage, is the operating voltage. Now that's not something we've talked a huge amount about, but on this capacitor you can see it's rated, it's got its capacity, and then it's got an operating voltage. It can go up to 25 volts. Now you need to be aware of that. Like I had the diagram of the bladder inside there. If you put too much pressure into that vessel, it's potentially going to break or explode. And it's exactly the same for capacitors. You no doubt have seen many video clips on YouTube of people either connecting these up in the wrong polarity or to a very high voltage and they explode, and it can be very dangerous. So that's the one criteria you do want to look at, is the voltage. The next thing is the ESR, or the equivalent series resistance, because ultimately for the most part you probably want your capacitor to have a low ESR. There might be some applications where that ESR is going to affect your circuit. So that's another criteria you want to have a look at. You want to see what operational temperature they work at. If you've got it in a power supply and there's hot temperatures, you may have capacitors which are going to fail. And in fact, that is one of the big issues with these electrolytics, because they've got the dielectric, there's potentially fluid inside these, and these can rupture, or the fluid over time can ooze out or dry out, and that's going to change its characteristics, and that's where appliances or electronics potentially stop working. So the operational temperature is important, and then obviously, as you've noted, if you've got a frequency component, capacitance changes with frequency. So you want to understand frequency, and all of those you want to go and look up in a data sheet and then understand the type of capacitor that you want. And as I've noted, that electrolytics particularly, that is the one issue. If it's the one thing you're going to kind of look at when you're troubleshooting electronics, first off is to literally go and look and see whether they're bulging or leaking or whether they look old. Or the next thing is to understand how to troubleshoot that, and we'll look at that next. So the electrolytic, you want to, because of it possibly might leak because of age, you want to choose a good name brand. Be very wary. There are lots of cheapos out there, but if you want a capacitor which is going to last a long time and you don't have to go and revisit your electronics, or if you're replacing capacitors, replace them with a good name brand. Safety, what I wanted to highlight is that, obviously with a smaller capacitor like this, it can't hold a lot of charge, and it's at a relatively safe voltage of 25 volts. If this was fully charged up and you had to put these leads together, you're going to see a little spark. Nothing too dangerous. However, and this is a caveat, when I say put leads, be very careful about discharging capacitors. If you go and search on the internet, there are safe ways of discharging particularly larger capacitors, and you need to take note of that. Once you start getting to the bigger capacitors which are used on motors, like this one for instance, it's a motor starting capacitor or big power capacitors. As you can see, this one is rated for 220 volts AC. It's got a relatively small, a medium kind of size in terms of capacity. But imagine this was fully charged and you had to lay your fingers across that. That would bite you. You would get a nasty bite. And in fact, if you had to put your two separate hands, remember there probably potentially might only be milliamps coming out of here, but it only takes a few milliamps to go across your heart to stop your heart or cause an issue. So that's why I say be very wary. And now when we talk about these boost caps, and I say once I start ending off the video, I'll talk about the future of these. But here is a different case in point. These have huge capacity. This one is 1,500 farads. This one over here is 2,600 farads, but they are low voltage. Okay, so it's at 2.5 volts. And this other one is at 2.7 volts. Now, and here you need to use your common sense. What I'm going to tell you can do, don't do it because it still could be dangerous. But in this case, because it's 2.7 volts, if this was charged up, I potentially won't get any shock because it's a low voltage. Don't try this. Honestly, you need to be sensible. However, one might think, okay, fine, so if it's not going to give me a shock when it's fully charged, let me get some wires to discharge it. This capacitor will release hundreds of amps if not into the 1000 amps. In fact, this capacitor and this one over here, if you short discharge them, can release over 1000 amps, and that can do a lot of damage. It will melt things, it'll spark, it'll crackle. The capacitor could explode because of the quick release of energy. These can release high energy in a short space of time, but they're not designed to release energy as quickly as a normal capacitor. So that you certainly need to be wary about. So that's the safety aspect. Now in terms of fault finding tools, as I said, you can go and measure capacitance value with a multimeter, but it for the most part is going to be using DC, and as you realize, capacitance value can change with frequency. So if you want to measure correct capacitance value, ideally you need to have an LCR meter. Now this LCR meter does do ESR as well. Now why do I mention ESR? If you want to know whether a capacitor is faulty or not, knowing its capacity, even if it's still producing its correct capacity, doesn't mean it's potentially going faulty or already faulty. What you need for that in particular is a meter like this one, say, which does particularly measure ESR, equivalent series resistance. This one does as well. This one potentially can do it in circuit to a certain degree with some error margin. But measuring ESR, if you measure the ESR and you know the given ESR and the measured ESR is becoming very high or high, then that is a sign that potentially you've got a cap that's degrading and going faulty or is faulty. And that's where these tools become important in terms of if you're trying to diagnose and troubleshoot circuits which have got capacitors. Right, so before we end off, the one thing I want to highlight in terms of going back to the safety, I pointed out that I've obviously got this one capacitor which is a motor starting capacitor, and that is rated for 220 volts. I've got another one here which is rated for 440 volts. So if you have a closer look at that, you can actually see on there it says 440 volts, and you certainly wouldn't want to touch that if it's sitting at that voltage. You really need to understand how to discharge these safely, so certainly do beware. But in terms of going back to super or hybrid capacitors, now these come in various sizes. I have ones which look the same size as, let's say, an electrolytic like this, and I've started experimenting with like running devices off these. Now the future for supercapacitors and hybrid capacitors is potentially very interesting, because these can even today be used in hybrid vehicles. They use them in particular in the regenerative braking system, so that when vehicles are braking, they apply an energy into these, and then that energy is used, let's say, to accelerate the car to start it, to preserve either the main batteries or fuel. Now in terms of energy density, it's the amount of energy that can be stored in kind of the space, and the weight for this is still not the best. You're going to find your best energy density technology for the most part is lithium battery technologies. But they are in the lab, they are producing hybrid and supercapacitors now with lithium technology, which will literally start to have the same energy density as today's lithium batteries. And that's quite exciting, because that means like our devices like cell phones, electronic devices, even hybrid cars, that could be their main power source as opposed to normal batteries. The big advantage to that is that obviously the life cycle of these is long. You can have thousands of life cycles out of these compared to a battery. Also, charging them is far quicker. So where you may have a hybrid car that needs to sit in your garage plugged in and charging up for 8 hours, it might only take 1 hour, and that's huge in terms of hybrid car technology. You can now get to the point where you could even have an inductive plate or coil in a road, and you park the car over that in a parking space, and because the charging time is so short, potentially with this technology coming down the road, you could park your car over that, and while you're perhaps going out and doing the shopping, your car could be fully charged, ready for you to go without even having to pull into a kind of recharge station or recharging at home. Think of your cell phone. Your cell phone may take 2 to 4 hours to charge. If it had a hybrid capacitor or supercapacitor in there that could charge quickly, it might take 5 minutes. Plug in, 5 minutes or a few minutes later, plug out, fully charged, and you can use it for a whole day. And that can be of huge value. So I say the future certainly looks very interesting in terms of this technology. Anyway, I hope you gained some value out of this tutorial. If you do, please give it a thumbs up. That certainly helps me. And I'll catch you soon for the next video. Cheers.